So recapping inverse functions. In order for a function to have an inverse function, it must be a one-to-one function. That's probably a simpler way of saying it. In other words, it satisfies both the horizontal and the vertical line test. The functions can be either one-to-one or many-to-one. The other two are relations, so the one-to-many and the many-to-many are relations. But functions can either be one-to-one or many-to-one. It's the one-to-one that we're interested in to become inverse functions. And if it is, then what we should see is this. Whenever we substitute the inverse into the function, or the other way around, they should cancel each other out and we get x. How do we test? As I say, horizontal line test would be a way of visually seeing whether it has an inverse. Or, if we swap in the x and y values around and then make y the subject, we should end up with something that's unique. We don't end up with a situation where we say plus or minus or something like that. If you've got an odd function, the inverse function of an odd function will always be an odd function itself. That will always be true. However, an even function, if you think about it, will never have an inverse function. Because an even function's going to have reflection symmetry, and therefore it will always fail the horizontal line test. Domain and range. As I said, the x and the y's basically swap over. So if AB is on the original function, then BA should be on the inverse function. So basically the domain of the function becomes the range of the inverse function, and the other way around as well. The range of the function becomes the domain of the inverse function. Well, here's one we've been looking at recently. Y equals e to the power of x, which we know looks like that. Its domain's all real x. Its range is y is greater than 0. We also seen that the inverse function of that is the natural log of x. And the domain of that is x is greater than 0. The range and the domain do indeed swap around. And the range is all real y. Again, yes, they swapped around. And if we were to look at them both on the same graph, whenever we see a relation and its inverse relation, or a function and its inverse function, both the same, they should reflect in the line y equals x. That's what we should see. But of course, a lot of functions are not going to be one-to-one, but we still are interested in some type of inverse function. So what we have to do is restrict the domain, so we just get a piece of it that we can do it with. So we restrict it, so just that piece of that function is one-to-one. In other words, we've got to look at the picture and get a piece of it that's always continually increasing or continually decreasing. And then that would become one-to-one. A parabola, let's just look at that one. Y equals x squared, and clearly it would fail the horizontal line test. So as it stands at the moment, the domain's all real x and the range is y is greater than or equal to 0. No, we can't get an inverse function. We can get an inverse relation, but that's not what we're interested in. We want an inverse function. So we're going to restrict it. I want to get a piece of this curve which is always continually increasing or continually decreasing. I guess I've got two choices. I've gone for x is greater than or equal to 0, but I guess there's no reason why I couldn't have gone from less than or equal to 0. But what we tend to do is we try to include the positives rather than the negatives. So we tend to go with the positive values rather than the negative values, and certainly if we can get 0 in there, we try and get that as well. We keep it as close to the origin as we can. My range, taking that piece, doesn't change. I still capture all the y values, so that's a good inverse function that we could use. Swap the x and y around to see what it is. It is y equals x to the power of a half, or the square root of x. And if I was to draw it on the same graph, reflect it, and there's what we get, the top half of the parabola. Okay, here's an HSC one that they asked a long time ago now, but anyway, here it is. The classic bell-shaped curve, that pattern of a bell. It's got the equation e to the minus x squared. It's got 2 points of inflection, they're telling us. So that's where the curve changes concavity. So there's one over here on the left and one on the right. First thing it wanted us to do was find those x coordinates. Now, all right, we haven't technically looked at that idea yet, but when we do, what we'll see is the way we locate them is we want to see where the concavity changes. To do that, we're looking for when's that second derivative equal to 0. That will give us the possibilities. Means I've got to do some calculus here. e to the minus x squared. Differentiate it once, I get minus 2x e to the minus x squared. Differentiate a second time, got to use my product rule. Write down the first diff the second plus write down the second diff the first. There's our second derivative. So solving that is equal to 0, we get plus or minus 1 on root 2. Once we start looking at these things in more detail, what we would then do usually is we would go and confirm whether they are. These are just possibilities. In this case, I didn't need to because they told me it's got 2 points. And because I only got 2 answers, well, we can logically conclude that, oh, they are the 2 points. If I had ended up with more possibilities, then I would have to go and check and see which ones are actually the inflection points. But okay, we found the x coordinates. Explain why the domain of the function must be restricted. Okay, well that's what we're talking about. We need to get a piece of the curve that is 1 to 1. And so that's basically what I said there. And maybe I went overboard and I went, in other words, every value in the domain gives a unique value in the range, but that sort of explanation is what they're looking for. Find a formula for the inverse function. And they're going to restrict it. Our restriction is going to be the positives. Going with the positive. X is greater than or equal to 0. Swap the x and the y's round. And I want to make y the subject of all this. I end up with plus or minus. That's no good for the function, plus or minus. I want something that's unique. That's where the restriction comes into play. We restricted the domain of the original function to be x is greater than or equal to 0. Therefore, the range of my inverse function must be y is greater than or equal to 0. The domain and the range swap over. Now I can go back to the equation we came up with and I know which one to pick. It must have been the positive square root is the one I'm looking for because I want answers for y are greater than or equal to 0. So there's the inverse function that they're looking for. State the domain. Okay, now the other way around. The range of the original function becomes the domain of the inverse. They gave me a graph, so there's not a lot to do other than look at the graph and see what the range of the original one was. I can read off that, but now that's going to become the domain. So x will be in between 0 and 1, but not including the 0, because the original function had that horizontal asymptote at 0. Now sketch it. All right, I cheated. I just got mine and rotated it. But yes, you draw a reflection of that curve. It should end up looking something like that then when you reflect all those points through y equals x. The 17a, a recap on inverse function.